Feel like we are, we've got enough for a test. I am going to do a little more today and probably a little more Friday. I said the test would be Wednesday, right? I moved it to Wednesday. So I have part of Friday and Monday to review. But I want to do a little more out of this chapter. I think this chapter involves some ice tables, and I kind of went past ice tables from the previous chapter, so I think ice tables for the equilibrium stuff, I'm just going to put on the test 3. But I think we're in good shape generally for getting through the semester and covering the things that are important. So I'm going to slow down, and today will probably be short like it was Monday. I think Friday might be a little short too. I just don't want to get ahead of myself putting questions on D2L because I promised y'all those for practice. So I want to start a couple of things I want to do. Just as a reminder for something I did before break, before I got sick, if you had, this is for a weak acid, I told you we do this as a general description. A just means acid, any acid. And this is aqueous, H2O liquid, and then the proton pops off and comes over here, making H3O plus. And that'll be aqueous, dissolved in the water. And then you have whatever you had for the acid over here. I should have used for this H3. So an example could be this. Aqueous plus H2O liquid, H3O plus, and this would be. So this minus is just indicating it's one more negative than it would have been over here. And I used this polyatomic ion over here. And then just as a reminder, just like we did for equilibrium, where you would put concentration of products, concentration of reactants equals K in general. Meaning more specifically, I'm going to say Ka, this is kind of a review of something I did before. So if I did this one, I would go concentration of H3O plus, concentration of PO4 minus for the product, and then the reactants down here, I'm going to put and I'm not including the water because I said in the equilibrium chapter, if it's L or S, you don't include it. It's just for aqueous and gases you include. So this is just in the same way that the equilibrium constant tells you how far it's shifted to the right, though I should be doing this. For the acid-base equilibrium, or the acid equilibrium, it's the same way. How far do we go towards dissociating this acid to here is also described as a K. In this, instead of saying an equilibrium constant, we say it's the acid dissociation constant or the acid ionization constant. But don't worry about that vocabulary. It's almost literally the same thing as describing an equilibrium. Having said that, let me go back to something that's a little more fundamental. This is called, that was just to remind you of where this comes from. This is called pretty sure I mentioned this before, so this, but I didn't do much with it, the auto ionization of water. But what I mean is, if I have H2O, it will split a tiny amount of pure water, L for water, will split off into H3O plus OH minus. That will be aqueous, and that will be aqueous. A tiny amount of that happens, and I mean pure water. No acid or base is put in it, so you just have pure water. A very small amount of that water is going to do this just by itself. It's actually just like a property of water. It does this. Now, if I wanted to do a K value, in the numerator, I'm putting that in OH. And of course, this is liquid, these are aqueous, so I'm not going to include the liquid. So really, it's just that. When we call that KW, it means auto-ionization constant water. And if I stop there, it's a well-known value. And I should say at 25 degrees C, because it will shift a little bit with temperature. The higher the temperature, the more it shifts that way. Okay, what else do I want to say? So let me give you I don't want to write the fundamental over here yet. So let me use, so keep that in your back pocket. Let's say I have a weak acid, and its auto-ionization constant is, or no, let me just deal with, let's say I have a weak acid. And I have a concentration for that weak acid. This actually works for any acid, but we're going to deal mostly in weak acids today. And let's say my concentration was so if I had an acid, I put it in water, creating a concentration of the H3O ions of this, and this does mean molarity. If I did that, I took the negative log of it, or actually take the log and then multiply negative by negative 1. So I'll put it in the calculator, and I go 0.0012, and I'm hitting the, on my calculator, it's it's got a 10 here to say it's a log base 10. If I hit that, and I say equals, if I go log of 0.0012, my calculator gives me 2.92, negative 2.92. So I put this in my calculator, I hit the log key, that's what it gives me. But notice the definition says negative. It's really like negative 1 times the log, and it just takes this negative off if you do that. So the negative log of this is, and that's what we call pH. So kind of a fundamental way to write it would be pH, something you've heard of, pH, right? Equals the negative log You took chemistry before. You talked about pH before, right? Did you talk about this? Do you vaguely remember the concentration of the H plus is how you get the pH? Do you? I just wonder if they do that, go that far in high school. I'm sure they talk about pH, but did they show you how to calculate it?
I don't think so.
Okay. That's where it comes from. It's kind of arbitrary to do the log, but it's just like in a lot of situations, like the Richter scale and things, when you have this huge range, because I'll go ahead and say that KW is this, which means that, I'll come back to that. But if you had 14 zeros and then a 1, it's just more convenient to do it on the log scale for pH. And it's the same way with this. These huge ranges of concentrations that you can get, they're just represented better this way. But this also means it's worth writing this to make it more intuitive. pH this. To the negative pH. So two definitions that you can kind of stick together. So if you have the concentration, the hydronium, it's called the hydronium ion, the concentration of this, you can find the pH by doing log and then multiply by -1, and then you'll have the pH. If you have the pH, you can put this into your that's what I'm using on my calculator. For this, you can go 10 to the negative, 10 to the x is the key you use. So if I said, hey, I've got a solution that's pH equals 2.92, and I said, what is the concentration of the hydronium ion? What you're really calculating is 10 to the negative. This isn't negative, but you have to put a negative on there. And then if you hit the, if you put negative 2.92 in the calculator and hit that key, it'll pop out with, in this case, I'll work through some of these problems. Okay, so that's the definition of pH. You've probably heard pH mentioned before. Like I said, I'll do some of these problems. But there's actually another one. pH is referring to H+. Given that we represent the hydronium ion like this, it probably should be P instead of pH. It should probably be instead of pH. But this is just kind of a summary way to write it. pH. Per hydronium ion or per hydrogen, I think is what it means. But there's also POH, which is a negative log of OH ion, not used as often. So there's these two things that are related to each other. Okay. So if you know the concentration of this, then you can find the pH. If you know the pH, you can use your calculator to find that concentration. Okay. Autoionization of water. I'm going to finish this. And if I'm formal about it, I'll go negative log of Kw equals the negative log. I'm kind of doing a derivation here. That times OH But one of the properties of logs is, this is the same thing as, where did I put the negative? I'm not going to make you derive this. I just feel like I want to be formal. If any of you are mathematically inclined, this should be in parentheses, I think. Okay. You may or may not remember this as a property of logs, but something I can do if I have a log of this times this, I can do the log of this plus the log of this. Do you remember that from anywhere? You do? You've seen it before. What class was it in? Calculus? Okay, yeah. All right. So it's that weird part. And if you do that, what I'm really getting at, now if I go related to these, I could go P of kW, this P function, equals, negative log of the hydronium ion. Negative log of the hydronium ion is pH. Negative log of the OH ion, negative log of the OH ion is pH. And this is where we get, when you learned about pH, do you remember what the scale is? The minimum and the maximum on the pH scale? 0 to 14. And this is where it comes from. pKW is 14. That is, I guess I need to write this over here. KW, auto-ionization constant for water. Times 10 to the negative 14. So the pK of this ends up being 14, which means this one is 7. This one is 7. I guess the definition I want to write here, though, is equals. And again, I don't mind giving you these types of definitions on the test. I just felt like being formal about it. So for pure water, for pure water, pH equals 7 for pure water. So that means it's not acidic or basic. It's right in the middle of the scale of 0 to 14. The pH scale goes from 0 to 14. When it's right in the middle, that means it's pure water. That means it's not acidic or basic. So I want to say there. Yeah, okay. Or I should say it like this. An acidic solution has a pH less than 7. Neutral, meaning it's not acidic or basic, has a pH of exactly 7. And basic solutions have a pH that's greater than 7. So there. based on the pH scale. I included in here figure 14.2 if you printed it out. But that first column says that at the top, and it's got M for molarity. It's got 10 to the 1. Let's start at 10 to the negative 1. Because there's really nothing at 10 to the 1. If I said, here's the concentrations of the ion, this is just a scale though. So you can be somewhere in between these two values. But this means here's pH 1, here's pH 2, here's pH 3. These are very acidic. These are pH. And then right here at 7 is when you're neutral. You have exactly the same amount of acid as you do base. You have, at this point, it's 7. Those balance each other perfectly. So that's what we mean by neutral. Up here, is much greater. The concentration of H3O is much greater than the OH. That's really what we mean by acidic. There might still be a little bit of OH in there, but there's way more H3O plus than there's OH minus. And I'll just put 2 chevrons there to go as we start going up the scale. Still greater than the OH. But once you get down here, you've got H3O plus is now less than concentration of OH. Here, concentration H3 plus is much less than the concentration of OH. And then at 14, way less. In general. You follow that? And that's kind of what 14.2 is showing here. It's giving you concentration of H3O plus in this form. But it shows you the flip side. It shows you the concentration of OH. And you see right in the middle, you've got 10 to the 7 and 10 to the 7. And then once you get past that point and start going down, then you have higher numbers in the OH. Way down here, if you put an acid, like acids can exist in their powder form and you put it in pure water. If it's down here, you put a strong acid in there. If it's kind of in the middle here, you put a weak acid in. If it's kind of around in here, you put a weak base in. And if it's down here, you put a strong base in. The equilibrium stuff we talk about is in this range. Because strong acids go all the way. If it's a strong acid, we're going to go with that arrow. If it's a strong base, we're going to use that arrow. But if it's weak acids and weak bases, this is when we're doing this. Then it's an equilibrium rather than an outright reaction. Okay. Take 30 minutes. All right, so let me hit the ground with something here. Example. And this is just about calculating pH and concentrations. So if I put HCl in water, it will become, let me keep this consistent. In a bunch of water, I will get as a reaction a single arrow because it's a strong acid. Now, this is aqueous, that's liquid, aqueous, aqueous. You might think for an equilibrium constant, I'm going to go and that's a liquid, I'm not going to include it, but that's aqueous, so I'm going to go on the bottom. These don't have any coefficients, so we don't have any superscripts here. But because it's a strong acid, we really only do this when we have a double arrow and we have equilibrium. But if it's a strong acid, there's none of this left. That's literally zero, which means this is literally infinity. See what I'm saying? So we don't really have these for strong acids. And we don't have the corresponding base constants for strong bases because they go all the way to completion. So my point is, every bit of the HCl I put in there that made it this many moles per liter HCl, they all reacted to go over here. So I do have literally, this is literally the concentration of H3O plus. You with me? Because every bit of the HCl does react and we get that much HCl plus. Or H3O plus. Okay, so we're asking for the pH. So to find the pH, that's the concentration, so we have to go negative log. If you do that, you will get 2.92. I'll bet these scientific calculators will let you do the times 10 to the negative 3. If I were doing it old school, I would put that in my calculator. 1, 2, 3. And take the log. Meaning I would put that in the calculator. And then hit this key to find the pH. Okay. I didn't like to check your learning for this one.
How did you know, again, that the concentration of the hydronium is 1.2 times 10 to the negative? Is that 2?
This?
Yeah, how did you know that?
It was given in the problem.
Oh, okay.
What I'm saying is, go back to, last semester. If I said I have, the molarity. We were dealing in molarity kind of all semester, even in the kinetics chapter. But that means and I always say, I don't know why we invented the M. When we do density, we say grams per milliliter. I mean, I don't know why we had to have an M. But that's literally what the M is, moles per liter. And if I wanted to be more, even more, sort of proper for this, I would say, HCl solution. So you would see this written in a problem last semester, and then to work with it in some calculations, I always tell my students to just go through this process, hit this, that's how you want it to do your calculation. But we're literally talking molarity. So if you put that many moles per liter into an HCl solution, that means since all that HCl becomes H3O, it's a one-to-one relationship. Every bit of the HCl you put in there created one H3O plus. So therefore, whatever molarity you would have calculated for the HCl, that's how many, the molarity of the HCl.
Will we always know that like all of the HCl is like used for the?
If it's a strong acid,
Okay.
then all of it reacted. Contrast that. Oh yeah, that's what I'm going to do Friday. Contrast that with, does anyone have that example? Yeah, I have an example that will put that together. Maybe I should go ahead and use something like that. Okay, that's for a strong acid. Let me try for a weak acid. Let's do. I want to save this problem. I'll go ahead and make this problem. And this is a weak acid. What is the acetic acid concentration? So that's acetic acid, and we write it this way because once it goes into the water, it becomes this. The part of it that ionizes splits off into that H plus, and then this is the negative part. That's acetic acid, and if I did it like this, H2O liquid, that's aqueous. Now I'm going to use the double arrow and have some H3O plus, aqueous, plus CH3, CO2 negative. All right. Ignoring the question I'm trying to answer here, do you see that as a reaction? This is the acid. This is its conjugate base. This hydrogen popped off and went on here and made H3O plus. You with me? All right. And then if I did this, the Ka for this, CO2 minus over so now we're dealing with this because it's a weak acid. Now, if we could somehow get this, then we could say what the pH would be. You see what I'm saying? Before it was easy because every bit of it became this. But if I told you some molarity that this is, how many moles of this that I put into the water, not all of this became H3O plus. So when you're dealing with a weak acid, it's a little more complicated to find the pH. You're going to need the Ka and some other concentrations. So this problem I'm stepping up to here is acetic acid. This is that's what I'm calling acetic acid. This polyatomic ion is called acetate. And then you have water and hydronium. So what if I had a problem that said, what is the acetic acid concentration? I'm going to put this in water. I don't want to phrase this. So they give you this in the problem. If this concentration equals 0.050 molar, and they give you what if I give you if I tell you at equilibrium, that's the concentration of this, and I say that what did I say here? I don't have a problem for you guys to solve on this yet, but just to show you what you do for these, I think this is where I'm going Friday. So when you have a strong acid, it's easy. For this, you would have to be told, this is how many, this was the solution mixture that I mixed up. Let's say I put let's say I mixed it up like this. When I say acetic acid here in acetic acid solution, I'm saying I put 0.175 moles of this in some water. And then I tell you, once it reaches equilibrium, the concentration of this was this. And then I can say, so now what is the concentration of H3O? If the Ka value that you looked up or I gave you, this is part of the information you're given. Ka value here for that one was, I probably should have waited till Friday to do this. 0.8 times 10 to the negative 5. So let's put it like this. You're asked a question. Someone said, I mixed up. Here's what you're given. This is what you're given as the problem, without the equation. You're given this, meaning I tell you I made this molarity solution. But of course, not all of the 1.175 moles became H3O plus like it did with HCl. Not all of it will, because it's equilibrium. Only some of it does that. So you're given that as information, and you're told at equilibrium, this is how much of this we have. You would use an ICE table to find out how much of that was left, which I said I will do for test 3. The book doesn't do a good job of explaining the ICE tables. So you're told this, you're given this, and then you use an ICE table to find this. And then you're also told the Ka is 1.8. You're also told that. So what I'm getting at is the only variable left is to solve for this. So you're given this, use a technique we'll cover for test 3 to find this based on that. And you're also told what the Ka value is. Then you can find this. And if you can find this, then you can find the pH. See what I'm saying? But just put that in your back pocket for now. So pHs for strong acids and strong bases is what we're doing now. Let me let's do some more of those. I included in here a list of strong acids and strong bases, so you'll know when you're dealing with a strong acid or a strong base. Somewhere towards the back. Right there. Strong acids and strong bases. Okay, let's do this next one, please. Calculate the H concentration of blood. And then they tell you pH for blood equals 7.3. What that means is I thought this would go quick because I know these are simple. But the way to calculate this is this way. So you're going to put in pH. You're going to put in pH. Make sure my calculator doesn't move. So I'm going to put in my calculator. Negative 7.3. 0.3 negative. And then I'm going to hit the 10 to the x cube. Just remember you got to put this negative here. It's not listed here, but you got to stick that negative on there. Otherwise you'll get the wrong answer. Okay. 7.3 negative 10 to the x equals, the calculator says 1, 2, 3, 4, 5, 6, 7. Which is This one's only tedious because of all those zeros. So 5.1, 1, 2, 3, 4, 5, 6, 7. I'm making this seem more complicated than it is. Your calculator does all the work for these. If you just practice doing them, you'll be okay. Let me ask you another question. What is the pOH of blood? They've given us the pH. What is the pOH? So we can find the concentration of H3O plus in blood. Well, it's actually this simple. You got 14 there, you plug in what they gave you for pH, and you just solve for pOH. And then you could use pOH to find out the concentration of OH in blood if you wanted. It would be even smaller. Blood is slightly acidic. No, I guess it's slightly basic at 7.3. Again, KOH, it's in the list of strong bases. When you put KOH in water, it becomes, and this is a one-to-one relationship, there's no coefficients here. So whatever the concentration of KOH was when you made the solution, that's the concentration of the OH in the solution. It's sort of like when I said, I'll use 0. NaCl solution. You put your NaCl in it, and you have, let's see now, minus, and we usually say aqueous like this, but really this is just the process of dissolving. So if it was 0.055 molar NaCl, it was only that just at the instant that you drop the NaCl in there. The instant right after that, there's no NaCl left, but you have Na and Cl. But its concentration in Na plus is 0.055 molar because it was one-to-one relationship. So now the solution is 0.55 molar Na plus, and it's also Cl minus. See what I'm saying? So here, when we say that it's 0.0125 molar KOH solution, we're just saying that tells you how much KOH was put in there. But really, as soon as you put the KOH in there, it all dissolves because it's a strong base. And now you have that molar that. See what I'm getting at? So because it's a strong base, I'll deal with weak acids and weak bases Friday. Because it's strong base, that's the concentration of the OH. You follow me there? And since now you know the concentration of OH, you can do this to find the pOH. Without putting it in my calculator, they tell me it will be, if I do that in the calculator and then multiply that with negative, I believe the rule is, it's in the appendix and I haven't gone back to look at it. This is 4 significant figures, and that's why I'm keeping 4 here. Or no, this is 4 after the decimal, and that's why I'm keeping 4 here for the OHs. 0125, that's 3 significant figures. So they did it wrong, don't they? I think they should have just done that. Anyway, that's what example 4.6 says. If that's pOH, what is pH?
Or
it's 14 minus that. Whatever that is, 13. Is that right? 12.1. 14 minus 1 is 13. And then 13 minus 0.9 is, I think there's, I can't do subtraction in my head. Yeah, 12.1 is what they have. They have 12.10, so I might still be doing significant figures wrong here. Is it hot in here or is it humid in here? It is humid? Huh?
like both.
I was going to open that door, but the traffic's too loud out there when a truck goes by. This part's kind of a long walk too. I guess I'll do it. A little more derivation in theory. Weak acid go Ka. And then base, when we do this as a base, we go base plus H2O for Bronsted-Lowry. And then we go Kb, the base ionization constant. Plus. Okay. So let me use acetic acid again. CH3O2H. So analog to this, if I'm going to use acetic acid, which is this. Now what if I do this? Okay. So if I had this reaction, just let me point up here. If I have this as my reaction, and I said, look at this, and look at this, what are these to each other? They're the conjugates, exactly. So what I'm going to talk about now is the Ka value for this acid, and then the base ionization constant for its conjugate base. So that's really what I'm getting at here. But here's a specific example using acetic acid and then its conjugate base called acetate. All I'm getting at here is if you have, give me that as an example. Whatever. I'm going to continue with that. If you have two reactions, I'll show the plan. HA. All right. I'll just say if you have Ka for acetic acid times Kb for acetic acid, I'm going to write in the Ka. H3O plus. Times, and now Kb we can reduce this. If I cross out that and that, and I cross out this and this, I'm left with Ka times Kb equals which equals Kw. I meant to write that over here. But I did that at the beginning, auto-ionization of water. This auto-ionization of water. So we're just saying that when you have conjugates of each other, this is a rule you can follow. Ka times Kb, Kw. Kw is that constant that equals. Okay. So what I'm saying is, if you have the Ka value for something, and you want to know the Kb value for its conjugate base, you just use this constant and a little bit of division and you can find it. to save this last page. Now, I'll go ahead and mention 14.7. I need to say for this example, though, I have to talk about salts. Okay. If I said, before you took chemistry, I said, what is salt? You go, it's that stuff I put on my food. And I said, well, what is it chemically? Well, you might have already heard somewhere that it's NaCl. Strong acid plus a strong base. It's a single arrow because they're both strong. Will give me, and I'll say aqueous because you know that's dissolved, NH2O. Does that make sense? That's the definition of a salt for a chemist. It's ions that come from a strong acid and a strong base that make water, and you end up with what we call a salt. Here's another salt. HBr plus LiOH. Now we have LiBr. So a chemist is going to tell you that's also a salt, but you probably don't want to put it on your food. Okay. The thing about salts are, strong acid, strong base. If you put, I'm going to say, if you put that in water, I guess I should say aqueous, but really it all goes away because it's perfectly soluble. You have K plus aqueous, and you have Br minus aqueous. But here's the thing, now you have K floating around in water, and you have Br floating around in water, and you have to wonder what those will do in the presence of water. But because there is such thing as KOH and there is such thing as HBr, this is in the strong base list, this is in the strong acid list, then these do nothing in water. Let me put it like this. To be consistent, I probably should have said HBr plus H2O, and then I would show H3O plus here in Br. Yeah, well, let me do that. HBr plus H2O makes H plus Br. And because there's no equilibrium here, if you have this sitting in water, there's none of this. So if I put Br in water, there's no reaction with water that kicks it back this way. See what I'm saying? But if I put something else in water, here's another salt I can put in water. Let me do this first. CO3 minus. If I put that in water, I'm going to get now that's not a strong acid, but because that's a strong base, it's going to make all of that acid react and do that. So here's another salt. Now if I put that in water, let's just say I put it in water and I have those things in water now. And what I just said before, water is NaOH gives me plus in water, plus in water.
Yes, that's right. But it's a single arrow because it's a strong base. All of it reacts. There's no equilibrium. So if I had Na sitting in water, and here I got Na in the water by doing this throwing base in there, and it did this. Here I got Na in the water because I put this salt in the water, and it became this. But because this is a strong base, Na in water doesn't shift back this way once it lands in the water. But HCO3 does this. And that's not the strong acid. It's not in the strong acid list that I put in there. So that tells you, I should have a negative here. That tells you when you put this in water, some of this reacts with the water and takes back this way. Maybe I should have done this. So I'm explicitly showing the role of the water. So weak acid, you put it with some water, you do get this reaction, but it isn't complete. You still have some of this left over. You have this equilibrium. So the whole point is, if I put this salt in water, because this is the metal from a strong base, that's fine. It doesn't do anything further because it doesn't go back this way. But this, being a weak acid, has some of this action going on here. And I could also say, remember amphiprotic? Amphiprotic. CO3, H. Both of those things can happen. So if I put this in water and then this shows up in water, you've got two equilibriums that can go on there. You can have this go on with the HCO3 minus, and you can have this go on with the HCO3 minus. You see that? So the whole point of this final section is, example 14.7. I can kind of simplify this. If I go A, B, C, D. So I have these salts, and I say I put this in water. If I put this in water, the water stays neutral. If I put this in water, the question is it acidic, neutral, basic? This stays neutral because of KOH and HBr that I just described before. In this one, and really kind of ignore that one for now. What I want you to do is think about the ions these become, and think of as a first answer to this question. So I put this in water. Does that make that water acidic or basic? Or neutral? If I put this in water, it'll stay neutral because there's no backward equilibrium to these two ions when it comes to the acid-base interaction with water. Ignore this one for now. But this one, NaOH, strong acid. But HCO3 is amphiprotic and HPO4 is amphiprotic, based on stuff we've already gone over, right? So whether it's acidic or basic, you need one other thing. This book has you just always look things up in charts. Let me say this. For B, Ka for HCO3 and its Kb value. Okay, that's true for this one. And then for this one, the Ka value is generally what you can look up very easily. So assume you were given these values, the Ka values. Ignore that for now. All I want you to do for now is look for the amphiprotic ion for these types of problems. And assume that you have access to the Ka values. All right, the question is it acidic or basic? It's not going to be neutral. All right, the final step is that is and then whichever one of these is larger is tells you whether it's acidic or basic. So I'm just going to cheat and look at this. That's Ka for this. Kb for this. CO3 minus equals, using that formula, you can find Kb for this, and you would get which one of these is larger? Left or right?
Sorry.
It's a negative 8. Sorry, it's a negative 8. Okay, but it's same answer, right? Yes, right. The one on the right's the bigger. Do you see that? So that means this is going to be basic. If you put this salt in water, it will actually be a little bit basic because of the way this interacts with the water. You follow me there? I'm good at making things sound more complicated than they are. So I went through all that description, but this is how you would solve a problem like this. You look for the amphiprotic ion. It might not be an ion, so I just say amphiprotic part of the salt. No, it will be an ion because these are salts. So you look for the amphiprotic ion and assume you have a list of Ka values for a bunch of different amphiprotic ions. You can find the Kb and you can decide which one's larger. Whichever one's larger, if the Kb is larger, it's basic. If the Ka is larger, then it's acidic. This one ends up being, that's Ka. For this one, Kb, if you solve through here, ends up being so that's Ka and that's Kb. Which one is larger? This is the larger one. So this one ends up being a little bit basic too, because of the way the HPO4 interacts with the water. We'll review that again before the test. I think that's all I want to do. That last one, I tried to go ahead and do. I don't know, just leave that. I'm not sure what I'm going to try. Else I'm going to try to do Friday, but it won't be a lot. I'm surprised this took as long as it did. I just kind of went long-winded, I guess. But as long as I get these problems on B2L, then that'll be part of the test. If I can't, that'll be part of the test.